Imagine a future where our planet's energy needs are met, not by finite resources or intermittent terrestrial sources, but by an inexhaustible, constant stream of power from space. This isn't science fiction. It's the audacious vision of space-based solar power, SBSP, a concept poised to redefine humanity's relationship with energy. Space-based solar power, often referred to as orbital solar farms, represents a paradigm shift in energy generation. It involves the collection of solar energy in the vacuum of space, where sunlight is perpetually abundant and unhindered, followed by its efficient transmission to Earth. This revolutionary approach promises a future of clean, reliable, and limitless energy. Unlike terrestrial solar panels, which are limited by day-night cycles, weather, and atmospheric interference, orbital solar arrays operate in an environment of uninterrupted sunlight. In geostationary orbit, GEO, approximately 36,000 kilometers above the equator, a satellite remains stationary relative to a point on Earth, bathed in sunlight for over 99% of the year. This constant exposure ensures maximum energy capture, far surpassing the efficiency of any ground-based system. The absence of atmospheric scattering and absorption means the solar panels receive the full spectrum and intensity of solar radiation, leading to significantly higher power output per unit area. Once collected, the solar energy must be safely and efficiently delivered to Earth. This is achieved through wireless power transmission, primarily via high-frequency radio waves, specifically microwaves, or potentially lasers. The collected direct current, DC electricity, is converted into microwave energy by magnetrons or klystrons, then focused into a narrow beam by a large transmitting antenna. This beam is directed towards a ground-based receiving antenna, known as a rectifying antenna, which efficiently converts the microwave energy back into usable DC electricity. The rectenna's design, often a mesh of small dipole antennas, allows for high conversion efficiency while being transparent to sunlight, enabling dual land use. The pursuit of SBSP is a truly global endeavor, with leading space agencies, research institutions, and private companies across continents investing heavily in its realization. Nations like the United Kingdom, the United States, China, and Japan are at the forefront, each contributing unique technological advancements and strategic roadmaps. This international collaboration underscores the universal recognition of SBSP's potential to address global energy security and climate change challenges. The shared ambition to harness the sun's power from orbit is fostering unprecedented levels of scientific and engineering cooperation. The drive towards SBSP is fueled by its unparalleled benefits, addressing critical limitations of current energy infrastructures and offering solutions for a sustainable future. Its unique attributes position it as a cornerstone of future energy grids, providing stability and abundance. One of the most compelling advantages of SBSP is its ability to provide continuous baseload power. Unlike intermittent renewable sources such as terrestrial solar and wind, which are dependent on weather conditions and time of day, orbital solar farms can generate electricity 24 hours a day, 7 days a week. This constant output ensures grid stability and reliability, eliminating the need for extensive energy storage solutions or reliance on fossil fuel peaker plants to balance fluctuations. SBSP offers a consistent energy supply, crucial for powering modern societies and industries without interruption. Solar panels in space capture significantly more energy than their terrestrial counterparts due to several factors. The lack of an atmosphere means there's no absorption, reflection, or scattering of sunlight, allowing the panels to receive the full intensity of the solar spectrum. Furthermore, the absence of clouds, dust, and humidity ensures pristine operating conditions. This results in a higher power output per square meter of solar array, making space a far more efficient location for solar energy harvesting. The vacuum of space also offers unique thermal management opportunities, potentially enhancing cell performance. Beyond continuous and efficient power, SBSP offers profound environmental and societal advantages. It significantly reduces the land footprint required for energy generation compared to terrestrial solar farms, preserving valuable ecosystems and agricultural land. By providing a clean, carbon-free energy source, SBSP can drastically cut greenhouse gas emissions, mitigating climate change. Moreover, the ability to beam power to remote or disaster-stricken areas, independent of existing grid infrastructure, offers unprecedented energy resilience and humanitarian aid capabilities. It also opens new avenues for economic growth, job creation in high-tech sectors, and the development of advanced space technologies. While the promise of SBSP is immense, its realization is contingent upon overcoming significant engineering, economic, and logistical hurdles. These challenges, though formidable, are driving innovation and pushing the boundaries of what's possible in space. The initial development and deployment of SBSP systems represent an enormous financial undertaking. Costs are driven by several factors: the sheer scale of materials required, the high expense of launching mass into orbit, and the complexity of in-space assembly. Each component, from solar cells to power converters and transmitting antennas, must be space-hardened and ultra-lightweight, adding to manufacturing costs. However, ongoing advancements in reusable launch vehicle technology, such as those pioneered by SpaceX, are dramatically reducing launch costs. Furthermore, the development of in-space manufacturing and robotic assembly techniques promises to streamline construction and lower overall deployment expenses, making SBSP economically viable in the long term. Transporting the vast quantities of components required for a gigawatt-scale orbital solar farm presents an unprecedented logistical challenge. It necessitates numerous heavy-lift rocket launches, raising concerns about launch frequency, atmospheric pollution from rocket exhaust, and the potential for increased orbital debris. The assembly of these massive structures in orbit, often spanning kilometers, requires sophisticated autonomous robotics and advanced construction techniques. Solutions involve modular designs, where smaller, manageable sections are launched and then robotically assembled in space. Research into self-assembling structures and advanced materials that can unfurl or inflate in orbit is also critical to minimizing launch mass and complexity. The technical complexities of SBSP are multifaceted, demanding breakthroughs across various engineering disciplines. Power conversion and transmission. Achieving high efficiency in converting DC electricity to microwave energy and back again is paramount. Beam control precision is critical to ensure the energy is directed accurately to the rectenna, minimizing spillover. Atmospheric attenuation, especially during adverse weather, must be accounted for, potentially requiring adaptive beam steering. Thermal management. Space environments experience extreme temperature fluctuations. Components must be designed to operate reliably under intense solar radiation and the deep cold of orbital night, requiring advanced thermal control systems. Radiation. Hardening. Space radiation poses a significant threat to electronic components and solar cells, degrading performance over time. Developing radiation-hardened materials and shielding techniques is essential for long-duration missions. Mass and volume reduction. To minimize launch costs, every component must be as lightweight and compact as possible. This drives innovation in ultra-lightweight solar cells, deployable structures, and advanced composite materials. Regulatory and policy frameworks. Establishing international agreements for spectrum allocation, orbital slot management, and safety protocols for power beaming is crucial. Addressing public perception regarding microwave safety and potential interference with existing technologies is also vital. Despite the challenges, the global scientific and engineering communities are making remarkable progress, transforming SBSP from a theoretical concept into a tangible reality. Numerous projects worldwide are pushing the boundaries of technology and demonstrating the feasibility of this ambitious vision. China has emerged as a leading contender in the SBSP race, with highly ambitious plans. Their roadmap includes launching a small-scale test satellite by 2028, followed by a megawatt-level power station in geostationary orbit by 2035. The ultimate goal is to deploy a 1-kilometer-wide solar farm capable of generating gigawatts of power by 2050. Their focus includes developing high-efficiency solar cells, large aperture microwave transmission antennas, and advanced robotic assembly techniques. China's rapid progress and significant investment highlight their commitment to securing future energy independence through space. The United Kingdom, through its Space Solar Initiative, is actively developing technology for wireless power transmission and exploring the feasibility of a gigawatt-scale orbital solar farm. Their proposed concept, Cassiopeia, constant aperture, solid-state, integrated, orbital phased array, aims to deploy a demonstrator by the late 2020s with full operational capability in the early 2030s. The UK's strategy emphasizes modularity, robotic assembly, and the use of advanced solid-state electronics for efficient power conversion and beaming. Their work is a testament to the UK's engineering prowess and commitment to sustainable energy solutions. In the United States, the Air Force Research Laboratory, AFRL, is spearheading the Space Solar Power Incremental Demonstrations and Research Project, SSPIDR. This program focuses on modular, scalable technologies, including the Arachne Flight experiment, which aims to demonstrate key power beaming and thermal management technologies in orbit. Separately, Caltech's Space Solar Power Project, SSPP, recently achieved a significant milestone with its SSPD-1 demonstrator, successfully transmitting solar power wirelessly in space and beaming it to Earth. This project is testing various technologies, including a lightweight, flexible power transmission array, MAPLE, and high-efficiency photovoltaic cells. These initiatives underscore the U.S. commitment to advancing the fundamental science and engineering required for SBSP. Japan has been a pioneer in SBSP research for decades, with the Japanese Aerospace Exploration Agency, JAXA, leading extensive studies. Their long-term vision includes beaming solar power from space by 2025, initially with small-scale demonstrations, and scaling up to commercial operations by the 2040s. Japan's research focuses on high-efficiency microwave power transmission, precise beam control, and the development of ultra-lightweight, high-performance solar arrays. Their consistent investment and methodical approach have positioned them as a key player in the global SBSP landscape. The European Space Agency, ESA, is actively exploring the feasibility of space-based solar power through its Solaris initiative. This program is conducting comprehensive studies on the technical, economic, and regulatory aspects of SBSP, aiming to develop a clear roadmap for European involvement. Solaris is assessing various system architectures, power beaming technologies, and the potential for in-orbit manufacturing and assembly. ESA's collaborative approach, involving multiple European nations and industries, seeks to leverage collective expertise to overcome the remaining challenges and position Europe as a leader in this transformative technology. The sheer scale of orbital solar farms necessitates a revolution in space robotics. Remote-controlled and increasingly autonomous robots are being developed for every stage of SBSP deployment, from component transport and precise assembly to in-orbit maintenance and repair. These robotic systems will be crucial for constructing kilometer-scale structures with millimeter precision, performing complex tasks in the harsh vacuum of space, and ensuring the longevity and efficiency of the solar arrays. AI-driven automation will optimize assembly sequences, monitor system health, and even perform self-repair, minimizing the need for human intervention. Research into lightweight and highly efficient solar cells is paramount for SBSP. Traditional silicon cells are too heavy for large-scale orbital deployment. Focus has shifted to advanced materials like cadmium telluride, CDT, gallium arsenide, GaAs, and perovskites, which offer higher power-to-mass ratios and better radiation resistance. These next-generation photovoltaic materials are designed to withstand the extreme temperatures and radiation environment of space while maximizing energy conversion efficiency. Furthermore, innovations in deployable structures, such as inflatable or rollout arrays, are reducing launch volume and mass, making large-scale orbital deployment more feasible. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.